talk about the integrator amp. So I'll just make a reference to this and previous video just did now. So I just want to point out the difference between a difference. I can't even pronounce this word very well. I have to cheat there. But the one that differentiator, that's what it is. Don't convert it with the one that is subtracting. I want to make a difference between this one and the integrator. This one, you know that I want to talk about them. Okay, first of all, the capacitor was here, and the differentiator on the integrator, the capacitor will be here. I think that the major difference if you have two spots in terms of visual. So this will be here, and then that everything will be exactly the same. Make sure that I copied it the way it was, because I'm trying to copy it. So I'll have to go there and cheat again. So it's also inverting, so it's minus plus. Let me call this R1, call this one V in, and then call this one V out. So I'll just derive very quickly, but because it's almost the same question that we did, so I won't be, I hope I can last at least 2 minutes on this problem. Okay, let me just, why it's not going down? Okay, cool. I understand why it's ignoring me, because yes, I want to put this here, shrink it a little bit, and then start working. Current going here is equal to current going here. There's no current going in here. I won't be too much details because I'm repeating this. So we agreed that okay, V minus is equal to V plus is equal to 0, virtual grounding. That means V in minus V minus all over R1 should give us something called current in, and we already said this will be 0, so this is 0, so you have literally very less things to worry about. V in all over R1 should equals to current in. So let's look at current going out. Current going out here. Current going out is actually the current in the capacitor, and we did talk about how do we get a current in the capacitor. We had Q is equal to CV, and then we'll have current is equal to C dV in all over dt, and then this is our current, and then you can just copy it here, dV in all over dt. But now our dV in is what is that one? Okay. Okay, hope I didn't make any mistake. And now I can actually equate these. I think it's gonna be in here because it should be this from there. I think I'll be talking about V out because I want to have V out. So and then I can actually equate these two. It will be V in all over R1 is equals to. So I think it look like this, and current dV, this is voltage out. Just call it not all over dt, and I'm interested in it. Okay, what I'm supposed to do, obviously I'll have RC here, and V in is equals to dV not all over dt. But now if you remember very well, what was our should I say our focal point? Our focal point was this. So if it's stuck inside the gradient, I like calling it gradient because that's how it made sense. Someone was doing math. We'll have to integrate both sides, and if we do, remember here we're differentiating in terms of t. I'll just leave it like that. I won't even touch it because it's not a math class. It's just the integral of okay, 1 over RC integral of V in dt. So this would be the voltage coming out of this thing. But I think now you should spot something wrong, of which there is, because this is inverting. It's going in the negative side. There should be a negative out here. I just don't know where I lost it. I think it would be nice if you just go and find for me where I lost my negative. But there is somewhere I lost it. I just can't figure it out just now. Oh, thank you. I just don't find it, but hopefully you will. But there is a negative here. I just don't know where I lost it on the way, because it's inverting. So if you want the full proof, this is it. That's how you derive an integrator, because this one is an integrator, which that one was a differentiator. So thank you for watching. This is the end of the video. Don't forget to share with people who you think may need it, and don't forget to subscribe also.